Good afternoon, everyone. In keeping with the session name, I'm going to talk about some measurements for validation and monitoring of the system, in particular some of the on-site measurements we've been doing in networks over the last couple of years. So really I'm going to describe how we got to the situation where we're doing tests in networks from an organisation that's traditionally worked in the lab for the last 100 years, talk about how we took that technology out into the field, and then give you some examples of the work we've been doing on various networks, and then move on to what we want to be doing in this area in the future. Over the years, as I said, since about 1905, NPL has been providing the physical measurement standards for the UK, and in my area I'm particularly concerned with electrical physical units such as the watt and the volt and the amp AC, which is clearly my interest in the electricity industry. And at NPL, one of the main jobs I do is look at the traceability for electrical power. Now that mostly impacts people from the little meter they have under the stairs, which tells them their energy bill over the year. And what we do at NPL is we measure power to 20 parts per million. Now it's easy for me to throw those numbers around, but it might be useful to put that into some sort of context. And the picture of the England supporters on the right hand side is a picture of Wembley Stadium, which has got a nice new floodlight system. And if you were to consider what 20 ppm means in terms of the light from those floodlights, it's about equivalent to switching a small torch on against the background of the lights. So that's the sort of precision that we're measuring power to at NPL. You might ask, what do you need that for? Well, if you're going to start trying to define the revenue metering standard for power in the UK, you've got to start somewhere, and at every stage in the process until you get to that meter under the stairs, you lose some of that accuracy. So we're starting at around about 20 ppm, that very high level, measuring active and reactive power at all phase angles. Also in the lab, we've been looking at power quality over the last maybe 10 years, and the importance of that in product testing is very clearly defined by the European Union. Every product has to be tested for power quality, and we are the people who've put together the standards to ensure a level playing field for that testing, to make sure that commerce can exist with domestic product and industrial product compliance testing. So that's our traditional field, and really the move towards smart grids has made us think about how this sort of technology can be applied and indeed brought out into the laboratory, from the laboratory into the field environment. So to do that, we have built a number of pieces of instrumentation, and a lot of the work has been based around the precision digitizer that we have here. We've got a lot of experience in digitizing electrical waveforms that goes back to the 70s. Some of the earliest work on digitizing waveforms was done at NPL. And this system here, which there's a picture of it in the bottom left-hand corner, a digitizer system, allows us to take some of the algorithm work and some of the measurement work that we've done in the lab out into the field environment. Now this device is an 8-channel digitizer. It allows us to do 3-phase and neutral and various other things. Allows us to measure it. It has transducers to step the current and voltage level down. It has a GPS interface, so we can use it as a PMU. It has environmental telemetry, so that we can measure things like solar levels and wind speed and so on and so forth. And all of this can be controlled via the 3G network back at base to allow us to measure a number of things. So what I'm going to do now is show you some of the work we've done with this unit in the last year or so. And we're in the way of 3 case studies: one a retrofitted PV cluster in North Wales, one a high voltage DC converter link between Sweden and Poland, and finally a wind turbine measuring a quantity known as flicker, which I'll describe in a minute. So the first of those case studies was carried out in association with Scottish Power, where we went to a retrofitted PV site in Anglesey in North Wales, and you can see there on the right hand side a diagram of all the houses on the estate, and the little dots are retrofitted PV. This was funded by the Welsh Government, and the idea of the study we did was to look at the effects that this power, that this installation would have on the power quality on the LV network. and there was some monitoring done at various points by Scottish Power and also by us in the North substation there. And you can see one of the Scottish Power engineers, Ken Lennon, there with his very special rubber gloves on, fitting one of our transducers to the bus bars in this substation. This is something called a Rogowski coil. It's a split device which is effectively held together with Velcro, and Ken is wrapping it around the bus bar there so that we can measure the current flowing through those bus bars in the substation. And there are a number of findings which may interest you from this study. The first one may not surprise you if you're going to put PV in North Wales. The solar installation only generated about half the capacity as advertised, even on the sunniest days. So we correlated the power flow with the Met Office data for sun, and we could clearly see the correlations. And even when we were getting good solar radiation, we were only getting about half capacity. So someone's cost-benefit analysis may have needed looking at after that. There was certainly a rise in voltage across the feeder. Just 4 volts doesn't sound an awful lot, but it was working fairly near the statutory limits anyway, as is often the case. So that could be a concern, that the voltage rise. 1 volt at the stiffer end at the substation. Not substantial harmonic detection. We wondered if we'd see some of the converter harmonics, but they weren't particularly visible there. Indeed, there was a general improvement in current harmonics as you were getting clean generation from the PV. Some change in voltage unbalance as well, again quite small, but 2% is the statutory limit in unbalance. So a 1% change you could say is of some significance. And the other kind of interesting finding is that, of course, when these PV units are generating substantially, they're generating active power, and the DNO is left to supply the harmonic current and the reactive power against the background of this active generation. So that is something which is of some interest, perhaps, to the audience here. The second case study we have done recently is to look at the power quality in a high voltage DC link, and the one that we're working on is the one between Sweden and Poland. Now, I must confess, before I started doing this work, I didn't know that Sweden and Poland had any geographical closeness whatsoever, but they are in fact separated by the Baltic Sea, for those of you who are better in geography than I am. So this link goes across the Baltic Sea. It's a ABB installation, and it's a thyristor station, traditional station, and we installed our digitizer technology in 2 locations there to look at the power quality. We used some bushings on the high voltage transformers as a means of measuring wideband voltage there, and we've used some special shunts on the CTs which we've made up to measure the current. And some of the results from this show particularly a change again in voltage as the link operates. 2% step change one way, decaying slowly to -2%, which was kind of interesting finding. Changes in distortion on the link as the link operates. These things have got large converters, large thyristor converters, chopping up the DC to turn it into AC with big filter banks, which are major pieces of civil engineering. And one of the things that we want to find out from this study is how to measure the impedance looking into the grid so that filter designers can make a better job of filtering out those harmonics. And that's one of the main things that we're doing on this ongoing study, looking at the impedance of the network as the seasons change and as load and generation is brought on and off. And we were able to see a number of findings there, some change in non-characteristic harmonics. They're the ones that are not related to the chopping frequency of the converter, and also again some changes in unbalance. What was also interesting is that we found these effects at the point of common coupling. That's where the station is connected to the Swedish grid. But the operators were quite interested to know what was happening 100 kilometres away. So it's all very well to say that this station has this effect on the grid at the point of common coupling, but what effect does it have in say, Gothenburg or somewhere like that? So this brought through the idea of perhaps doing some wide area power quality monitoring using GPS to relate effects at this point to effects on the wider grid. So that's an interesting thing to do in the future. And the final thing I want to talk about is something called flicker. Now this is related unbelievably to the way the lights flicker when the voltage changes, and there's a whole lot of research gone into this phenomenon and psychological profiling on how flickering lights affects various people. It really is just a very fancy way of looking at voltage fluctuation. But all renewable plants needs to be checked for its effect on flicker, and working with Vestas, who are a manufacturer of wind turbines, and also a Danish lab, Trescal, we have been in the last few months doing a study on this wind turbine farm in northern Denmark, and there's my holiday pictures from a beautiful day at -16 degrees on the Danish coast in December as we installed our equipment there. And what we are looking to do is take measurements of voltage fluctuations at a full range of wind speeds from 3 meters per second up to something like 25 meters per second. And we're kind of relying on nature to provide that wind speed variation. So we have a whole set of remote measurements that we're taking, making bins of various wind speeds, measuring this very strange phenomenon known as flicker to this IEC standard, such that we can characterize these wind turbines for Vestas such that they can meet this IEC standard that I've listed there, which uses this very curious term called a fictitious grid, which allows you to make various adjustments to your measurements to take into account the impedance of the network at various points where the wind turbines are connected. And again, down the bottom there's a picture of our Rogowski coils installed on this wind turbine installation. Last slide is some of the future work which we hope will come out of this. I mentioned wide area power quality. This is the idea of a PMU in some respects, how power quality propagates around the network through the various transformer levels. Grid impedance I've also mentioned. That's a question of measuring how the impedance changes with frequency and also with season, such that people who are designing filters and people who are running models of networks can get some better information such that they can do better design. This leads to another thing that you can do with impedance measurement, perhaps has been mentioned today, dynamic rating of overhead lines. And by looking at the resistance change of the overhead lines, it's possible to perhaps give some estimate of the average temperature change in the overhead line, which could be useful for dynamic rating. Sensor networks and the whole problem of all of this data that's being generated, we've heard a bit about today. And Andrew from Strathclyde is going to talk in a minute. He may mention some of the work we've been doing with Strathclyde on a project which looks at optimizing where you put sensors around a distribution network. So instead of cluster bombing the network with loads of sensors, you pick the very best places. That must be an optimization problem. So if you can run the maths on that, you can say this particular node really needs a sensor, whereas that particular node doesn't. So you can reduce the amount of money you spend on sensors, and perhaps more importantly, reduce this huge amount of data and how to interpret it by cleverly placing your sensors. Perhaps using smart meters for the same process is another thing that we're interested in looking at. And demand response, there's a whole session on it in a minute. Some of the work we're doing with sensors is applicable to that as well. So that gives you a brief flavour of some of the things that we're doing at NPL on monitoring networks. Thanks.